get this microphone on me, I will tell you exactly that. There. Can everyone hear me well now? Excellent, excellent. So I just got to start by thanking everyone involved again. Galaxy Workshop's always one of my favorite conferences to attend, and everyone involved should be really happy with the work they've done. So I'd like to talk today about these little weird star balls, globular clusters. We know that these are old, dense, massive stellar systems that you can think of as perhaps relics of an earlier phase of star formation. They tend to be pretty small, on the order of parsecs across, pretty massive, a few tens to millions, or tens of thousands to millions of stellar masses, and pretty old. Of course, there are exceptions to all of these rules. And one of the reasons we really think that these might be critical tools for understanding galaxy assembly is that there seems to be a fairly tight correlation to the globular cluster systems we see within galaxies and properties of the halo that those globular cluster systems live in. For example, the number of globular cluster systems scales pretty linearly with either the halo mass or the stellar mass, as well as the total mass of that system. And the fact that we tend to find them out far beyond the stellar disk suggests that they have an assembly history more complicated than the simple stellar disk that we see. So this brings this question up that's been discussed for decades now. Can we use these globular clusters to both understand galaxy formation as a whole and to trace the evolution and assembly history of individual galaxies? There's also a connection between globular clusters and these things we see in the nearby universe called young massive clusters. They tend to have similar size scales, again on the order of a few parsecs, similar mass scales, up to about 1 million solar masses, and we find young massive clusters forming in what tend to be very violent environments. Starbursts, mergers, areas where the ISM pressure and the turbulence tend to be very high, which is what we would expect from observations like the ones Reinhardt just presented, as well as countless others, the cosmic noon ISM to look a lot like. So we can ask ourselves, is this Redshift 0 birth site of young massive clusters, which looks quite similar to the kind of clumpy, disturbed galaxies we see at Redshift 2, ultimately a present manifestation of the past phenomena that led us to produce the globular clusters we see today? Well, in order to understand how these globular clusters evolve and test this question, we have to have a number of pieces in our theoretical framework. We need a model for how these things form. So for example, what is it that causes one parcel of the ISM to form a dense cluster, whereas another forms diffuse field stars? We need a model for how these clusters evolve while they're still in the disk. As clusters pass by molecular clouds and clumps of gas, spiral arms, etc., they can be shocked and experience tidal heating. We need a model that includes the effects of cosmology, namely the merger history of a galaxy, because that's ultimately what would then kick these globular clusters out into the halo, where they would then evolve more slowly through evaporation. So really you need three critical pieces. You need a model for formation, you need a model for tidal evolution, and you need that all put together in a cosmological environment. And that's what brings us to E-MOSAICS. The E in E-MOSAICS stands for eagle, because these are a set of 25 cosmological zooms drawn from the eagle volume, resimulated using a model called MOSAICS that captures the effects of globular cluster or star cluster in general formation, as well as evolution. So some of you are probably already quite familiar with the eagle model, but just to go over what the basic prescriptions are in there, is that it's a set of subgrid models that are specifically tuned to fit the Redshift 0 stellar mass function, M star M black hole relation, and size mass relation. So all of the subgrid parameters that go into the feedback, star formation, and AGN model have been tuned through a tremendous amount of work to fit these specific scaling relations. Everything else then falls out as a prediction of this model. These ones, however, are the input parameters you can think of for this model. And the way they do this is they include a metallicity-dependent star formation and feedback efficiency that's then coupled through this target temperature feedback model. Basically, you store up feedback energy until you have enough to deposit it without facing major overcooling. The MOSAICS side of the model includes, as I said, two pieces, a model for cluster formation and a model for cluster evolution. The cluster formation model assumes that cluster formation efficiency increases with increased pressure. This is empirically fit to match the observations we see in the present universe of young massive clusters. So you can see here in the example of one of these E-MOSAICS galaxies, the cluster formation efficiency drops as you go from high redshift down to low redshift as the pressure of the ISM decreases. Is that me? Sorry, not me, thank goodness. There's also the effect over which the maximum size scale a GMC can collapse onto is set by the tomb ray mass of the galaxy. And once again, in these higher turbulent star-forming galaxies that we see at high redshift, you end up having a maximum cluster mass that's quite a bit larger than the maximum cluster mass you can form at low redshift when your disks are more shear dominated and the tomb ray mass within the ISM has dropped. So what we do is we use these pieces to Monte Carlo sample a Schechter initial cluster mass function and populate star particles with globular cluster tracers. Now, if we just populated them, we would get a completely incorrect result because we know that clusters experience tidal evolution from both internal processes like two-body relaxation, or technically three-body relaxation, tidal evaporation, which is the slow tidal evolution they experience with the halo, and tidal shocks, where close encounters between the disk environment and the cluster can impart a lot of energy. We can evaluate all of this by simply looking at the tidal tensor and taking different components of it. And what you can see if you look at the evolutionary history, the tidal heating rate or the mass loss rate of three example clusters is, for one thing, one of the critical things that can keep a cluster alive is if it moves from a high tidal heating environment to a low tidal heating environment. This blue curve here is a cluster that's kicked out by a merger. Or it can form in a fairly low tidal or a low heating environment and stay there. This is a globular that was formed in a dwarf, which was then accreted and stayed within the halo. Or these globulars can be disrupted and not actually make it to redshift 0. This is a globular that stayed in a very, very high tidally intense environment and lost all of its mass by about redshift 2.5. But also it's important to see there is huge time variation in here. This is an incredibly stochastic process. And if you zoom in here, you can see that just on the order of mega years or so, you can have order of magnitude variations in your tidal history. This means you cannot do accurate tidal heating as post-processing. Unless you're willing to dump out tens of thousands of snapshots, you need to calculate these things on the fly. So we've already seen from a couple of publications that have come out now that the E-MOSAICS simulations reproduce a number of critical globular cluster scaling relations, such as the specific frequency, the metallicity distribution, and the spatial profile of the globular cluster systems. But I'd like to show you now a particular application to actually use these things to trace galaxy assembly. So it's been proposed for a long time that by looking at the age-metallicity plane of stars and globular clusters, you can disentangle where certain things formed, where they ultimately come from. And so we can actually do this with the globulars in the E-MOSAICS project. The colored background you see here is colored by the halo mass of all of the stars in the E-MOSAICS, or in the EAGLE simulations. The overlaid dots here are globular clusters from one of our galaxies. And you can see that, well, after I tell you, these are not open circles. These are colored points. So these globulars do actually trace quite well the halo mass of the galaxy that they formed within. So you can then go to the real Milky Way and place our own globular clusters in this plane and use that to infer the galaxy mass in which those globulars formed. And from that, reconstruct the Milky Way's merger tree. And from that, we've found that you can identify the Sagittarius dwarf. We identified before the first Gaia Enceladus paper even came out, the globulars that we now believe are part of the Gaia sausage or Gaia Enceladus. And also a third most massive progenitor that hasn't yet been discovered that we're dubbing the Kraken. This was the largest merger that the Milky Way has experienced that we're actually able to pick out. And it was a merger with a 10 to the 9 or so stellar mass object. So there's a lot of things that you can do with this project, with this kind of data set, and even more are on the way. Hopefully we won't have to actually sell our souls to the devil to get this, but we'll do the best we can with souls intact. I, in particular, am interested in where these things are forming. I'm working on the birth environments of the globular clusters because there's been many different proposed mechanisms for how you can construct these globular clusters. Maybe they form in very exotic environments like the first halos to collapse or colliding substructure. And we know that in E-MOSAICS we have a population that looks roughly like the population we see in the Milky Way. So what kind of birth environment do these things have? For example, do they form in situ or ex situ? We can see from the E-MOSAICS globulars that roughly 2/3 of the globular clusters in all of our halos form in situ. That is, the halo that they form in is the most massive halo at that redshift. They're the trunk of the merger tree. And this is true whether or not you're looking at the globular clusters we see today or things that we would see today as globular clusters if they hadn't experienced any mass loss. So this doesn't seem to be an effect of disruption, but instead an effect of just the formation process alone. We also see that relatively few globular clusters are actually formed in mergers. It's been proposed by quite a few different people that only during major mergers can you reach the high pressures required to form globular clusters. But we're finding that we actually form roughly 2/3 of our globular clusters in gas that has never been shock heated, about 20% in gas that's either been heated by feedback or passed through a virial shock, and only about 15 to 20% in mergers, of which only about 10% are 1 to 4 or larger, what we're categorizing as major mergers. But it's important to note that there's great variation galaxy to galaxy. For example, if you were to select our most violent merger here, Galaxy 10, you might think that more than half of globular clusters form in mergers. Otherwise, you might select one here and think none form in mergers. So it's important to have a statistical sample and not simply one really high resolution object to understand the assembly of globular cluster systems. So if we dig down into the ISM and look at the kind of environments in which they're forming, we're finding that the majority of the globular clusters, which again form around redshift 2, form in very gas-rich environments with gas fractions locally of about 90% or so. The pressures they experience are also high, but not necessarily as high as the 10 to the 7 K per cubic centimeter that have been proposed as being absolutely necessary to form these things. They're typically forming in a few 100,000 Ks per cc, about 100 times higher pressure than the Milky Way. So this is telling us that these things are forming in the dense tail of normal star formation and the kind of standard star formation you see right along the stellar mass to halo mass relation around redshift 2. This is the kind of galaxy you form a globular cluster in. A dense, turbulent, disrupted disk fed by cold streams. Now, I'll just quickly point out that there are well-known problems with the E-MOSAICS with the EAGLE simulations, and we're now working on a next step to include explicit ISM cooling, a new model for star formation and feedback, as well as an improved cluster formation model based on a couple of the work of a couple of grad students and another postdoc working with me in Heidelberg. And this EMP, or empirically motivated physics, versions of the simulations should be ready in the first generation in the next year or two. I'll leave my conclusions there. Thank you.
Thank you very much, Ben.
Thank you.
Do we have any questions?
Yes, got the job.
Yes, we got lots of questions. Okay, how about Nir?
Hi. So you'll probably be able to answer this with EMP MOSAICS, but I'll ask a preliminary question. I think it's been shown that all the galaxy formation models, such as Illustris and Eagle, that have these very low density thresholds for star formation, predict very different distributions of where stars are forming.
Yeah.
In particular, they're a lot less clustered, and it's been shown to affect cusp core transformations. Now, especially you were looking explicitly at where globular clusters are forming. Do you imagine that will change dramatically?
Absolutely, absolutely. And it'll also really heavily impact the evolution, too, because these smooth, effective equations of state smear out your ISM, which means you don't get quite as dense globular clusters, which will reduce the impact of tidal shocks. We suspect that the tidal shocks from the ISM are too weak in E-MOSAICs.
All right, Andrew?
You talked about strong time variability of the tidal forces these globulars are experiencing. Is this happening shortly after they form in nearby clouds? I'm just trying to think of
Almost always.
Trying to understand the evolution of globulars around the Milky Way. It's not all obvious to me there'd be very strong time variability.
Once they get kicked into the halo, it's very smooth and steady.
Okay,
The strong time variability is almost always while they're still within the disk, because you've got all of these things that allow them to drift relative to the gas, and anytime you pass a dense clump, you're going to feel a tidal force.
Okay, one last question from David.
Are you able to predict the dispersion in the metallicities of these different clusters in the different environments that come out of your simulations, and with that useful probe of what might be really happening in terms of where they came from, and et
Do you
cetera?
mean cluster to cluster or within a single cluster?
Both. I don't know.
Cluster to cluster, yes. Within a single cluster, no. We don't have a model for the internal. Basically, all of the clusters have constant metallicity within them. But internal cluster to cluster, yes, and there already are a couple of papers out on this. So I think Marta Reina Campos has done this. Yeah.
All right, thank you. Let's thank Ben again.